My goal today is to help you understand Jahn Teller effect. Dear students, myself Dr. Digna Varghese. Contents: Introduction, Jahn Teller effect, is it out and is it in distortion? Examples: static and dynamic Jahn Teller distortion. We have seen the various electronic spectra of different complexes like chromium hexafluoride complex and chromium trioxylate complex and chromium triethylene complex, and the spectra is different for each complex. From this, for ML6 perfect ML6 molecule, there is octahedral symmetry, and for chromium hexafluoride complex having octahedral symmetry. When we are changing this fluoride with the oxalate or ethylene diamine, we know ethylene diamine and oxalate molecule act as chelating ligand. By this, the symmetry changes or reduces to D3 symmetry. If two of the ligands in perfectly ML6 molecule is replaced by other groups such as X2, if cis or trans isomer is there, cis MX2L4 has C2V symmetry and trans MX2L4 has T4H symmetry, and trans CREN twice L4 giving D4H symmetry. From these examples, the perfect octahedral symmetry is for pure ML6 molecule. When it is substituted by the chelating ligands and it undergoes or reduces the symmetry into D3 symmetry, if two of the ligands from the ML6 molecule is replaced and cis molecule is having C2V symmetry, trans molecule having D4H symmetry. If simply we are changing a ligand from the ML6 complexes, the octahedral symmetry reduces to lower symmetry molecules. We know the for CREN3 plus complex having D3 symmetry, and one of the ethylene diamine ligand is replaced by two other ligands such as fluorine or any other ligands, the symmetry changes to D4H symmetry. The alteration in energy levels when changes from octahedral to tetragonal symmetry. In the case of octahedral symmetry, there is the terms are here, the non-degenerate A level and the T2G triply degenerate levels are here, and each T terms will be split into an E and A or B terms. 6 transitions are observed instead of 3. In an octahedral symmetry, there can be 3 transitions. 3 transitions can be possible from A to T2 and A to T1 and A to T1P levels, and these transitions can be possible. But instead of this, when the symmetry changes to D4H, each triplet or T term is split into E and A or B terms. So 3 into 2 gives 6 energy levels. So 6 transitions can be possible. Okay. So 6 transitions are observed instead of the 3 in D4H symmetry, and the transitions can be shown here. The electronic spectra of the 6 transitions can be shown here, and the values assigned for each transition is for B1G to 4EG, that is 18,400 and 18,400 centimeter inverse, and for B1G B2G there is 21,500, and for B1G to 4EG that is 25,300, and for B1G to 4A2G that is 29,300, and for B1G to 4A2G that is acts as a shoulder 41,000, and for B1G to 4EG that is 43,655. And from the octahedral symmetry changes to lower symmetry, the number of transitions also increases, that is the number of energy levels also increases. That means alteration in energy levels occurs, that you have already studied in orbital diagrams. Okay, now the term Jahn Teller effect. Explaining in this slide, the Jahn Teller effect is a geometric distortion of a non-linear molecular system that reduces its symmetry and energy. It is an important mechanism of spontaneous symmetry breaking in molecular and solid-state systems, which has far-reaching consequences in different fields, and is responsible for a variety of phenomena in spectroscopy, stereochemistry, crystal symmetry, molecular and solid-state physics, and materials science. This distortion is typically observed among octahedral complexes, where the two axial bonds can be shorter or longer than those of the equatorial bonds. This effect is dependent on the electronic state of the system, and this effect can also be observed in some tetrahedral compounds. In 1937, Hermann Jahn and Edward Teller postulated a theorem stating that stability and degeneracy are not possible simultaneously unless the molecule is a linear one. In regards to its electronic state, Hermann Arthur Jahn was an English scientist who worked on quantum mechanics and group theory. And Edward Teller, he is an Hungarian-American theoretical physicist who is known as the father of hydrogen bomb. This leads to break in degeneracy, which stabilizes the molecule and by consequence reduces its symmetry. Because of Jahn Teller effect, that break in degeneracy, which stabilizes the molecule again and by consequences reduces from higher symmetry to lower symmetry. Jahn Teller theorem states that for a non-linear molecule in an electronically degenerate state, distortion must occur to lower the symmetry, remove the degeneracy, and lower the energy. Thereby, stability of the molecule increases. Determine which octahedral complex will be subject to Jahn Teller effect by considering the ground state degeneracies and the configurations having non-degenerate ground state degeneracies are D3 having 4A2G, and D5 high spin having 6A1G, and D6 low spin have 1A1G, and for D8 having 3A2G. These terms having non-degenerate ground state energies. Thus the spontaneous Jahn Teller effect are expected, and these having no Jahn Teller effects. From this configuration, the ground state term is noted, and for those having non-degenerate ground state energies, those configurations having non-degenerate ground state energies having no Jahn Teller distortion. The spontaneous Jahn Teller distortions having thus obtained for other configurations like D1, that is 2T2G, and for D2 3T1G. D4 high spin having 5EG, and D4 low spin having 3T1G, and for D5 low spin having 2T2G, and for D6 high spin having 5T2G, and for D7 having 4T1G high spin and 2EG low spin, and D9 having 2EG. These all configurations show Jahn Teller distortions. Which octahedral complex will be subject to Jahn Teller effect means those having non-degenerate, those configurations having non-degenerate ground state energies show no Jahn Teller distortion, but the other terms having the other than non-degenerate ground state energies show Jahn Teller distortions. That is the basic condition. Okay. For a perfect octahedral symmetry, we know the symmetry of this octahedral system is octahedral. When we are changing from this ML6, one of the ligand from the ML6 molecule, the symmetry will be reduced, and there is alteration in energy levels also occurs. There is change in electronic configuration occurs, and this causes also a distortion. Distortions are, in the case of ML6 molecule, we are considering the z-axis, that is representing through this ligand ML system, and distortions are of two types. One is elongation. Elongation means the electrons, this ligand containing the z-axis, is moved away from the metal center. So the bond length of this ML on z-axis and ML on the positive side of the z-axis, or above the plane of this ML4 system and below the plane of this ML4 system, this bond length increases by the elongation of the z-axis. That means elongation occurs here. Okay. And there is other distortion can be occur, that is compression. That means the ligand on the z-axis move towards the metal. This also changes energy of the system, that is move towards the metal center, that is compression. So there is different electronic configurations occur, because as the elongation from the pure octahedral symmetry of this z-axis containing ligands, the bond length increased. This means that the Z containing orbitals undergo less repulsion between the metal and the ligand. When the z-axis approach towards the ligands in the z-axis approach towards the central metal ion, this means that the energy, there is a large repulsion between the metal and the ligand electrons. So this normally occurs different electronic configurations. The geometrical distortion of molecules and ions, that is related with certain electronic configurations. This means that the distortions in octahedral symmetry, perfect octahedral symmetry, the octahedral OH is the symmetry, and regular octahedral complexes with regular octahedral geometry are expected to form when all the ligands are of the same kind and it creates an angle 90 degree. But there is distorted octahedron. If it is compressed, that means the ligands on the z-axis move towards the central metal ion. So a distorted octahedral system is due to the compression of the ligands in z-axis. There is another types of distorted octahedron by the elongation of the ligands on the z-axis. These two distortions can be created or expected to form when the ligands are of different kinds also. So for a pure octahedral system, we are expecting when the ligands are approaching towards the metal ion, due to large electron-electron repulsion between the metal and the ligand systems, and the 5 degenerate p orbitals on the central metal ion split into two types, that is triply degenerate system having lower energy d2g orbital, that is dxy, dyz and dxz, and the orbitals along the axis having the higher energy, that is dx square, y square, dz square. This d orbital splitting we have already studied. And after when there is any distortions occur in the system, there can be change in energy levels of the system, that is the doubly degenerate Eg orbitals can be split into two, and the triply degenerate set can be split into two, that is again in the doubly degenerate form and a singly non-degenerate form, and non-degenerate form. And this means that the Z containing ligands is here, that is tetragonal symmetry, and dxy having the higher energy. In this case dz square have the lower energy and dx square y square having higher energy. Tetragonal distortion from octahedral geometry often occurs even all the 6 ligands are the same. If all the ligands are the same, we are normally expecting up to this crystal field splitting, but when we are checking its electronic spectra, we are getting more than 2 transition or 1 transition. There is some other possible transitions that we can see in the Auger diagrams. That is due to the other distortions, that is due to tetragonal distortions here. If there is any change in ligand from the ML6 system, definitely there is tetragonal distortion occur. So here the T2G system, that means triply degenerate orbitals, e.g. doubly degenerate orbitals, and T2G contains orbitals like dxy, dxz and dyz, e.g. containing orbitals is dx square, y square and dz square. The distortions will cause or just leaves the particular degeneracy of the T2G, and Eg levels are not degenerate, they are further splits. If any distortion occur, the T2G and Eg orbitals not remain in the same way as in the crystal field splitting in the octahedral field. They undergo further splitting and forms a tetragonal symmetry or tetragonal distortion. The splitting will cause loss in degeneracy and attain lower symmetry and lower energy. If the orbitals T2G or Eg in octahedral symmetry of a non-linear polyatomic molecule are degenerate, the degeneracy is determined by distorting the molecular structure to attain lower symmetry and thus lower energy. In a polyatomic molecule, the T2G remains as the dxy, dxz, dyz orbitals for a polyatomic molecule. In a degenerate state, and Eg remains the dx square y square dz square orbitals that have equal energy. But when a distorting molecular structure attaining, then this degeneracy is lost, that can be split into according to the energy of the molecules, and Eg can be again split, and to attain lower energy, by this lower energy the molecule attains stability again. Okay, actually the five degenerate orbitals are splitting in order to attain stability of the molecule. Okay, conditions for Jahn Teller effect. Tetragonal distortion from octahedral symmetry ML6 often occurs even when all the 6 ligands of a complex are the same. We are expecting when ML6 is for the same ligands containing the same L ligands, we are not expecting that any distortion, but in some cases there is all the 6 even if all the 6 ligands are the same, there can be tetragonal distortion happens. Two L groups that are trans to each other are found to be either closer to or farther from the metal ion than are the other 4 ligands. If two L groups that are trans to each other, that means the axial z-axis containing ligands are either closer to the metal ion or away from the metal ion than the other 4 ligands. A distortion of this type is actually favored by certain conditions by Jahn Teller theorem. By this distortion, according to Jahn Teller theorem, the symmetry reduces to lower symmetry, the energy reduces from higher to lower, and also attaining stability, and the degeneracy also removing from the system. Asymmetrically filled orbitals of a nonlinear molecule will show Jahn Teller distortion to remove degeneracy. Asymmetrically filled orbitals means if there is some T2G1 that is asymmetrically filled, T2G3 is somewhat symmetrically filled, T2G3 and EG2 that is symmetrically filled. So asymmetrically filled electronic configurations or orbitals containing electrons will definitely show Jahn Teller distortion to remove degeneracy. Consider an octahedral complex hexachlorotitanate 3. In this complex, titanium is in the D1 species or D1 state, and the ground term for D1 is a 2D. 2D can be calculated from using the term simple formula 2s plus 1 Lj, and 2s plus 1 is the total spin multiplicity, and L is for the total orbital angular momentum, and J for the total angular momentum. In the case of D1 species, there are 5 d orbitals and 2, 1, 0, minus 1, minus 2. The electron is present here, and therefore 2 into 1 by 2 for the spin multiplicity plus 1, that is equal to 2s plus 1 is equal to 2 here, and L is equal to 2 for the orbital from this value, and J is equal to to L plus S to L minus S. And L value is 2, S equal to 1 by 2, and here 2 minus 1 by 2, and we get two values for J, that is 5 by 2 and 3 by 2. This is less than half filled state, so lower value is taken. So the term is 2s plus 1 value is 2, and L is equal to 2, 0 for S, 1 for P, and 2 for D. So the term is D, 2D, and 3 by 2. This is the ground term for D1 species, and here it is true. That is, ground term is calculated by 2s plus 1 Lj. 2s plus 1 is the total spin multiplicity, L is the total orbital angular momentum, and its value 0 for S, and 1 for P, 2 for D, and 3 for F, and J is equal to L plus S to L minus S. And 2s plus 1 value is 2 into half plus 1 is equal to 2, and L is equal to 2, and J is equal to L plus S to L minus S. 2 plus 1 by 2 is equal to 5 by 2, and 2 minus 1 by 2 is equal to 3 by 2. So the term is 2D, 3 by 2. In an octahedral field, 2D term splits into T2G and EG, and 2T2G doublet T2G term is the ground state, and it is triply degenerate. The Jahn Teller theorem would predict a slight distortion in complex, slight compression of the axial ligands at low temperature due to Jahn Teller effect. The evidence shown from the electronic spectrum, there is two absorption bands or peaks separated by 1400 centimeter inverse, that is due to the Jahn Teller effect. The distortion is slight compression of the axial ligands. This was also supported by EPR results, electron paramagnetic results, which are consistent with a tetragonal compression. In this complex, this is just like ML6 system. Same 6 ligands are here, but the symmetry is not octahedral symmetry because of slight compression of the axial ligands, that is tetragonal compression here. So there is instead of one band, there is two absorption peaks are obtained due to Jahn Teller effect. This results agree with the EPR result. For some D1 complexes, the Jahn Teller splitting is not of sufficient magnitude to produce sufficient bands in the electronic spectra. In the case of hexa aquo titanium 3 ion, for which the two absorptions appear as one broad peak with a lower energy shoulder. In this case, two absorption peaks like a lower energy shoulder. This is also due to the tetragonal distortion. Jahn Teller distortion in D1 complexes. The energy T2G is level is splitting into dxy, dxz, dyz, here dx square, y square and dz square. It is in the compressed form because the compressed means the Z ligands are moved towards the metal ion. So the orbitals containing Z axis have higher energy than the other orbitals. So dz square is higher in energy than dx square y square and dxz dyz have higher energy than dxy. In ML6 complexes that are susceptible to Jahn Teller distortion have octahedral configurations that involve asymmetric electron occupation of either Eg or T2G orbitals. The former leads to Eg to considerably more pronounced distortions than in the T2G level. If Eg level is more asymmetrically filled than the T2G level, it is more pronounced for distortions. This is due to the Eg level is much more involved in the sigma bonding than in the T2G orbital. Hence, the complexes Eg1 and Eg3 configurations often exhibit substantial distortions. The strongest evidence for the Jahn Teller effects in transition metal compounds comes from the structural studies of solids containing the D9 copper 2 ion. There is two types of Jahn Teller distortion: static Jahn Teller distortion and dynamic Jahn Teller distortion. Complexes have measurable wave bond length differences, that is copper complexes are shown here, some chromium complexes are, or manganese complexes are here, and there is a short distances and long distances are shown in the table. And this in this copper fluoride complex, the compound exhibits short distance at 193 and long distances at 227 meter. And in the case of octahedral complexes, this also shows some measurable bond distances, but in the case of some complexes there is no measurable complexes at measurable bond lengths at room temperature, that is undergo dynamic Jahn Teller distortion. Static Jahn Teller distortion means complexes have measurable bond length differences. Some other complexes have no distortion can be detected in the room temperature crystal structure. Dynamic Jahn Teller distortion means at low temperature crystal structure shows distortion and spectroscopic data consistent with the tetragonal geometry. Jahn Teller distortion can oscillate from one orientation to other. At low temperature there is some bond length can be measured, but at a room temperature it can oscillate from one distortion to other or one structure to other structure, so the bond length cannot be measured. Such distortions are known as dynamic Jahn Teller distortion. Jahn Teller theorem. For a non-linear molecule in an electronically degenerate state, distortion must occur to lower the symmetry, remove the degeneracy and lower the energy. In the case of Z out, that means elongation. In the case of, from the table we can see that the copper fluoride complex, this is an octahedral complex and undergo Z in distortion. Octahedral means in this complex we are the copper is attached to 4 fluorine atoms, but in the crystal lattice it is attached to other 2 fluorine atoms. So the coordination number of copper in this particular complex is 6. The similar complex is Na2CuF4. This is an octahedral system, but it's elongated. Distortion, tetragonal elongation occurs. In the case of potassium complex, potassium copper tetrafluorocuprate potassium complex, in this axial compression occurs, compressed distortion occurs. In the case of chromium fluoride complex, in this elongation occurs. Chromium is in the +2 oxidation state. The elongation is like this. The xy axis containing orbitals undergo larger repulsion or higher in energy. So the dxz, dyz have lower energy than dxy, dz square have lower energy than dx square y square. So here the Jahn Teller distortion in copper 2 complex, that is hexafluoridocuprate 2. In this the elongation, tetragonal elongation occurs. So the Z component, orbital having the Z component having lower energy than the other 3 orbitals. So the energy level diagram is dxz, dyz, dxy, dz square, then dx square y square. The D9 system, copper 2 system, always show Jahn Teller distortion, either compression or elongation. In the case of D8 system, that is nickel 2, only one way of filling the orbitals, so not degenerate and no Jahn Teller distortion. In this case D8, this is symmetrically filled orbitals and non-degenerate orbitals, so there is no Jahn Teller distortion. In the case of T9, there is two possible ways of filling electrons in the Eg level. One is in the Tx square y square 2 and dz square 1, and in this case dx square y square 1, dz square 2. So there is two possibility, and distortion, Jahn Teller distortion is observed always for D9 system. And in the case of D4 and D7, a fewer support on Jahn Teller distortion in high spin D4 or low spin D7 complexes. Chromium 2 and manganese 3 compounds have been found to be distorted in some compounds. Hexacoordinate manganese 3 compounds have shown that their spectra can be interpreted in terms of elongation along the Z axis. In the case of complex COCN5H2O3-, which has an axially elongated structure. In these cases, the Jahn Teller distortion, the evidence for the Jahn Teller distortion is obtained from the electronic spectra. First from electronic spectra, later from or second from EPR results. Jahn Teller distortion, in this we can see the tetragonal distortion, that is elongation for an octahedral complex. Elongation means the Z-axis ligand is moved away from the metal ion. So the splitting diagram is like this. The Z orbital having lower energy because the influence of the ligand towards the metal ion is reduced here due to the elongation or bond length increasing. So the energy level diagram is dxz, dyz lower in energy than dxy, than dz square, than dx square y square. So the electronic configuration in T2G6 EG3 means, in EG3 elongation means dz square. The electrons filled first in this level, lower level, that is EG3. Here already filled 6 electrons. 1, 2, 3, 4 and 5, 6, 7, 8. Lower energy level dz square, and then later the electron in the dx square y square orbital. That is the electronic configuration in tetragonal distortion. And so this is also known as Z out case. Z out. That means d orbitals with Z components are stabilized. Here stabilized and here also stabilized. So it is Z out system. Z out system. Z out means elongation occurs. That is Z axis containing ligands move away from the metal ion. Okay. And second distortion is compression for an octahedral complex, and here the compression means the axial ligands, the ligands on the Z axis are moved towards the metal ion. That means the ligands are more closer towards the metal ion. So there is large repulsion occurs and the Z containing orbitals undergo higher in energy. So the orbitals dxz, dyz and dz square have higher energy than the xy containing orbitals. So the electrons can be filled, the 9 electrons can be filled in such a way that first in dxy to here, then dxz, dyz, so T2G6, then EG3, then filling in the lower energy dx square y square and dz square. So the electronic configuration in compression means T2G6 EG3, that is dx square y square 2 and dz square 1. So this is a Z-in system or Z-in state. That means the Z containing ligands are moved towards the metal ion. So the Z containing orbitals or Z components are destabilized. That means that is higher in energy. Okay. So the electronic configuration, it can be this tetragonal distortion or tetragonal elongation can be further verified by EPR spectrum or EPR results. If the ligand is present in Z axis or axial axis, it will expand, the bond length is increased. When moved toward the outside is called Z out distortion, and the reversed is called Z in distortion. In Z out distortion, the repulsion between the electrons in the metal and ligand orbitals is decreased due to elongation of Z axis. Therefore, the electrons in Z axis containing electrons dz square, dxz and dyz orbital is lower in energy than the other orbitals. For Z in distortion, the repulsion between the electrons in the metal and ligand orbital is increased due to compression of Z axis. Therefore, the electrons in Z axis containing electrons, that is dz square, dxz and dyz orbital is higher in energy than the other orbitals. In the case of octahedral copper 2 complex, that is hexanitro or N-nitrito cuprate 2 ion, which exhibit the full range of static and dynamic Jahn Teller effects. In the case of various nitro complexes shown here, these three can be shows the tetragonal distortion, that is elongated one or elongated Z out distortion occur. In this case, copper 2 anions are elongated. In the case of K2Pb, copper 2 anion undergoes pseudo compressed geometry, Z in distortion. And in the case of same complex, the cationic species is changed here in these complexes, so the structure is also different. In these cases, axially compressed octahedra is obtained at room temperature, but actually these are dynamic average of the two tetragonally elongated structure. So at low temperature it is the tetragonally elongated structure obtained, but at room temperature it shows the axially compressed octahedra. Molecular orbital diagram for the Jahn Teller distortion. The combined form, one is Z in and the other is Z out distortion. We are already discussed this. Jahn Teller effects in chelates. No discussion of the Jahn Teller effect in coordination compounds would be complete without including the special features of chelated compounds. The very nature of the chelated ring tends to restrict the distortion of a complex from a perfect octahedron because the ligand will have a preferred bite or a distance between the coordinating atoms. In this case, the bite or the distance between the two coordinating atoms, here ethylene thiamine, the two coordinating atoms are nitrogen here, so the perfect octahedron, because the ligand will have a preferred bite to the metal atom. In the case of the stabilization, there is a conflict between the stabilization from the Jahn Teller effect and chelate geometrical requirements is found in the ethylene diamine complexes of copper 2. Most divalent transition metal ion form complexes with ethylene diamine by stepwise replacement of water. In this case, it's an Ml6, MH2O6 2+, and ethylene diamine form MH2O4 En twice En 2+, and MH2O4 En. To this, ethylene diamine is added, MH2O twice En twice 2+, MH2O twice En twice 2+ ethylene diamine is added, and we get an octahedral complex Men thrice 2+. In each step, it has associated with an equilibrium or stability constant K1, K2, K3, which measures the tendency for the formation of mono, bis, tris ethylene diamine complex. The values of these constants for the ions manganese to zinc show a rather uniform trend to gradually decreasing from manganese to zinc from the left to right across the series, that is the Irving-Williams order. The copper 2 ion provides a striking exception, being remarkably unstable in the case of tris ethylene diamine complex. Okay, in this case, this is unexpectedly showing the stability decreasing stability. And this lack of stability for the tris complex can be traced directly to the tendency for a 6-coordinate D9 ion undergo distortion. In the case of bis-ethylene diamine complex, that is Cu En twice H2O twice 2 plus, can distort readily by letting the two water molecules move out from the copper and leaving the two ethylene diamine rings relatively unchanged. In contrast, the tris ethylene diamine complex cannot distort tetragonally because without straining at least two of the chelate rings. Okay, the tris in the bis complex, it is can distort easily because of the two axial water ligands. But in the case of tris complex, the ethylene diamine is axially occupying. Until there is no distortion occur, if without straining at least two of the chelate rings. Okay. It is possible that the constraint of a chelate ring system can prevent tetragonal distortion altogether, but the resulting perfectly octahedral complex will lack the stabilization inherent in Jahn Teller distortion. In the case of copper bipyridyl hexafluoroacetylacetone complex, which is tetragonally distorted, there is 2 longer bonds and 4 shorter bonds. So it is tetragonally distorted. Both bipyridine and hexafluoroacetylacetone are chelating ligands. These are chelating ligands that can bind through nitrogen and oxygen to the copper 2 center. The longer distance is at 200 or 199.8 picometer, that is approximately 200 picometer, and the other is with the 230 picometer. So the two remaining oxygen atoms form copper oxygen bonds, which are some 33 picometer longer than the shorter bonds of the copper nitrogen and oxygen bonds. This indicates that there is severe Jahn Teller distortion. Whenever there is a bond length difference in an octahedral system, there is any 4 short bonds or any 4 longer bonds or any 2 longer bonds, this means that they are tetragonally distorted. In the case of copper ethylene diamine, bis-ethylene diamine water diaquo complex, in this we have already seen here, and there is long axial copper oxygen bond, that is copper and water molecules 2.60 angstrom, and short copper nitrogen bonds in the ethylene diamine from the ethylene diamine ligand, that is 2.03 angstrom. So this is tetragonally distorted and its elongation occurs. And in the case of copper En thrice 2 plus, there is short in plane 2.07 and long axial 2.70. In this case, the distortion Jahn Teller effect occurs if this chelated ring undergo strain. Otherwise, there is no distortion. Thank you so much for your interest and attention.